Okay, welcome AP Chemistry kids. We are starting chapter 12, which is a chapter on chemical kinetics. And when you think of chemical kinetics, or you hear the word kinetics, that is another name for rate. And rates are part of our everyday lives. We have a speed limit that we have to abide by. So that is a rate because it's a distance traveled per unit time. You might be asked to, monitor your heart rate. That means that it's how many beats you have per minute. And you've been in many classes that, especially like in math classes, whenever you're talking about a rate, there is always a time unit associated with that. So when we look at chemical kinetics, it is the area of chemistry that concerns reaction rates. So when we talk about reaction rates in chemistry, usually we are looking at a concentration of a reactant, how that changes over time, or we are looking at how the concentration of a product changes over time. So how we would illustrate that would be that a rate would equal a change in concentration. And for this example, I'll just look at the reactant because that's pretty typical of what happens. I'm going to put that delta sign there, which you guys know means a change over a change in time. So how the concentration of a given reactant will change over time is how we define reaction rates. Reaction rates then could be if you were able to look at a concentration here of a reactant. So let's say we're looking at a concentration of a reactant at time 2, and you could also look at the concentration maybe at time 1. So versus and then of course over the change in time. We will do this in a lab on Monday. We are going to look at how crystal violet will change over time. And crystal violet is going to be this deep purple color. When we react it with sodium hydroxide, it will fade. So we will look at the concentration of how that change will happen over time. And we're going to use the spectrophotometers to do that. So that will be a really interesting lab. I'm going to have you guys remember the bracket means concentration in molarity, which is either moles per liter or M. Whenever we're looking at concentration rates, we're looking at reactants or products that are being considered. But typically, chemical reactions, we look at the product or the reactants are typically what we like to look at. So here is an example of a decomposition reaction of NO2. And NO2 then will decompose into nitrogen monoxide and oxygen. You'll notice that we have some data here. And the other thing to know, I'm going to go back here, the other thing to know about reaction rates is that rates have to be determined experimentally. You cannot figure out a rate just by theory. You have to do laboratory experiments to make that happen. So you will construct a laboratory experiment where you get to say, I'm going to look at concentration over time, or I'm going to look at the concentration and measure the rate of change. So they are things that you as the scientist will develop this experiment. You get to control the concentrations. You get to basically control the parameters of what that experiment would say and what it would mean. So here we've got nitrogen dioxide reacting with nitrogen monoxide and oxygen. And at time 0, so this would be at the very beginning of the reaction, before we allow the decomposition to happen, you would have a concentration of nitrogen dioxide of 0.01 molar, and you have not made any of the nitrogen monoxide or oxygen yet, so those concentrations are 0. After 50 seconds, the concentration of the NO2 has decreased, you'll notice, and the concentration of the NO has increased, and the concentration of the oxygen has increased. And it's asking us to find the rate at which NO2 decomposes. So we can then say that a rate would equal the concentration of NO2 over the concentration, or I should say the change in concentration of NO2 over the change in time. So to do this, I would say that the concentration of NO2 at time 50 seconds, because remember a change is always the final minus the initial, and then I'm going to be subtracting the concentration of NO2 at time 0 over 50 seconds minus 0 seconds, which would be that change in time. So I'm going to plug in what I have here, which would be 0.0079 molar minus 0.0100 molar over seconds. 50 seconds would be what's in our denominator. So what you will notice is you will get a value that has a negative sign, 4.2 times 10 to the negative 5. And this unit would have a unit of molarity over seconds, or you could have it M over S. Okay, so those are all ways that we would show that they're, the unit for the rate. This is interesting. The fact that it is negative indicates that you are decreasing in your reactant concentration. So just bear that in mind. It's not a negative rate per se. It is just the fact that you're decreasing in concentration. If we were looking at products and observing the products, how the products changed over time, the rate would then be positive. Also, when you're looking at this M per S, and you should know that this could also be moles per liter per second. So you may see a unit like that as well as an option for rates. Okay, so what happens here is we've got, and I'm going to see if I can get this to move here. There's something called an instantaneous rate, and the rate that we had done before would be considered an average rate over the time between 0 and 50 seconds. Would that rate always be consistent at a 4.2 times 10 to the 5 molarity per second? It may not, and it is just the average over that time period from 0 to 50. We can calculate something called an instantaneous rate. And an instantaneous rate is a rate at a particular time, and you can find out and read more about this on page 558, I believe, in your textbook. Or you can look for this picture of this graph, and that's where they're talking about instantaneous rates. But what you will use is you'll use the slope of the tangent line at any given point. So if I were to, let's see if I can get this bigger. If I were to make this bigger, and I know it's blurry, but we look right here at this specific point, the point right there, that would be, draw a tangent line to that, and then you find the slope. And remember, you find slope by taking, oops, there, let's see if we can erase this part of it. This is the first time I'm using this iPad for my thing here. Let's get that organized. Let's see if we can get this a little bit more centered. There we go. And you'll notice that if you take the rise over run, that might be a little bit clearer. If you take the rise over the run, that's how you get the slope, and you would find the rate of the slope of the tangent line. There's also something very interesting about what's happening here with this. Let's see if we can get this color in here, and we still have this fine pen. But I'm just going to highlight, or kind of like just highlight this green area here. That's pretty sad. Let me get rid of this. Let me actually just maybe use the highlighter. You'll notice that, let's see if this will work. You notice that as we are looking at this yellow line, here we go. Oh, I guess it's just something I tap rather than, oh, there we can draw. Okay, as we're looking at that green-yellow line, or greenish line that I've now highlighted, this will represent the reaction. So this is the same reaction that we were talking about. It is NO2. And as you're looking at this line, you notice that NO2 is decreasing in concentration. You'll notice that we would have this line here, which notice how similar those look. You could almost say that they're reciprocal from each other. You've got the decomposition of NO2 and you've got the production of nitrogen monoxide. And if we were to look at the stoichiometric ratio from the equation that we have here, so let me get to this color here, and we look at that right there, we notice that the rate of decomposition or consumption, if you will, of NO2 is equal to the production of NO because of the stoichiometric coefficients are exactly equal. Okay, they're 2. All right. Now take a look at this oxygen, and so we'll highlight that kind of in a pink. So we'll just try to stay. This is representing the rate of the oxygen. Notice from the equation that oxygen wasn't in a 1-to-1 mole ratio. It was actually half of what that mole ratio was. It was a 2-to-2-to-1 ratio. So there's less oxygen in that stoichiometric relationship there. But this is also an important key, that the rate, as we look at, oh, this one is okay. So as we look at the rate of consumption of NO equaling to the rate of production of NO, the rate of consumption of NO2 equaling to the rate of production of NO, they have the same stoichiometric relationship, right? But then the oxygen, the rate of the oxygen production will be twice that of the NO. You make only 1 mole of oxygen for every 2 moles of nitrogen dioxide decomposed. Therefore, that will be produced at a rate of 2 times. So bear that in mind as you're looking at reaction rates as well, so you can get some info from that. This is an example of what a rate law looks like. We will basically state that the rate is equal to something called a rate constant times the concentration of whatever we are observing, usually it's reactants, to a power, and that power is called the order. And what we're going to be, spending time in this class is looking at how that order will change. It could be first order reaction, a second order reaction. You can have fractional orders, although we won't see them here in this class, but they can exist, and you can have a fractional order. You're not going to see it much, though, in this class. And my time is almost up, so I want to finish this video with the idea that there are 2 types of rate laws that we will be discussing. There is the rate law, which we call a differential rate law, and that expresses how rate depends on concentration. So how rate and concentration will change. There's an integrated rate law that expresses how concentration depends on time. And how you are going to deal with which rate law we're talking about, differential or integrated, it's going to be based on the type of data you are given in a problem. So in this problem, you would maybe be given concentrations, and then you would be giving rates. So you will see something like molarity per second. So they're actually calculating, or they're giving you the rate of how fast something changed over time along with the concentration. And here for integrated rates, you would be given a concentration, and you would also then have a column of time, of how time is changing, how the concentration is changing. So that is the first video that introduces Chapter 12, Kinetics, with rate laws. And good luck.